So how the rearrangement will complicate this problem? With the question is, I'm going to give you two questions here. I'm going to show you how things can be done. This question here, you get ethanol replacing this chlorine makes this one. So that's easy. We expect, methanol is not a good compound, so it's not an SN2 reactions. We got the halogen chlorine pops out as a chloride. We get the carbocation formed here. But the thing is that can be captured by the solvent immediately. Then you get to make this one. So that's a regular substitution product. But the thing is, this one, you got the tertiary picture right next to it. So hydrogen shifts can happen. Hydrogen move over there, you get the tertiary carbocation. Then that one, captures it, you are making rearranged product. So two things happen at the same time. In a way, I would expect that is a major product because that makes a tertiary carbocation more stable than this one. So this probably happened better. So that is kind of a very easy thing to see, and it's about rearrangement. But this thing is actually something more than you expect. So let's say this is a molecule we start from. You get the iodine sitting on this carbon. So that ethanol again is a bad nucleophile, not SN2. Iodine lead, you get the carbocation. Primary carbocation is a least stable. These things looking for immediate relief. And then the hydrogen in the adjacent carbon almost move immediately, you get the tertiary carbocation. Tertiary carbocation is good. So I'm not saying that that's bad. It's good carbocation. And then solvent molecule, ethanol, will capture the carbocation, you end up producing this one. This is already a rearranged product. But what about that one? Why the 6-member ring becomes a 7-member ring? What happened there? I'm not saying that this is a most stable product, but sometimes you actually having that produced small amount. We are asking you to explain how that happened. So this is a kind of different thing. When I'm not showing this one, if I'm asking what will be the product, I'm expecting this. But the thing is, this question is not asking what is a major product. This question is asking that also forms, even though it's a minor product. Explain to me how that formed. That's what this question is about. It's a different way of the making question. That's the reason why it's a proposed mechanism. That wasn't easy because that's a major product. We expect it to happen this way. But how it makes that? So skeletons change from the 6-member to 7-member. So this is kind of a product of the rearrangement. So now you have to look at rearrangement different ways. This primary carbocation is really bad, right? It's really bad. Hydride shift is fast. So we expect most of them go that way. But I told you earlier, hydrogen is not the only thing that moves. Carbon can move as well. This carbon can also shift too. It's slower. That's the reason why that becomes a major product. But it's just possible. When is carbon shift there, meaning that it's creating this bond, that bond, it's breaking that one. So that's why these bonds are gone. If there's a 1, 2, 3, 4, 5, 6, 7-member ring with this carbon being a carbocation. So that becomes like a secondary carbocation in a 7-member ring. And this secondary carbocation captures the solvents, then you end up having this. The 7-member ring is probably less than the 6-member ring. And then this is much slower the carbon shift. But this is possible. Even though it's a small amount, this is possible. That's the reason why the rearrangement can make something very bizarre. So you should look out, because it's all relevant for the carbocation. The carbocation is what makes it difficult for the SN1 chemistry. That's a main point differentiate from SN2 and SN1. And the most importantly, you need to